In this video, we'll discuss two more tools, local regression and generalized additive models that help us model nonlinear trends. Let's start with local regression. The idea behind local regression is to fit regression models in small localized regions of the predictor, using only a nearby subset of the data to do so. In this figure, the local regression method is trying to make a prediction at about x equals 0.05. We see that the dark orange points are contributing to a local fit at this point, and the gray points are left out. The dark orange points are used to find a line of best fit in this small region. Usually, this best fitting line is found with a weighted least squares approach rather than the unweighted least squares approach used in ordinary linear regression. In the weighted least squares approach, the idea is that data points closest to the target point of x equals 0.05 should contribute more, should be weighted more, in determining the slope of the line, and points that are farther away should be weighted less. The shaded distribution illustrates the weighting scheme. The height of the distribution indicates how much weight a data point at that x-axis location is given in the weighted least squares estimation. Once the local line of best fit is obtained, we use it to predict at the current value of the predictor to obtain the function estimate at this point. Repeating this process for a grid of x-axis points gives the estimated function in orange. The estimate is fairly close to the true function in blue, which happens to be known in this case because the data were simulated. An example of the process for another target point is shown on the right. Here, the local weighted least squares approach gives a fit that slopes downward. Overall, this approach is pretty similar to k-nearest neighbors regression, but instead of averaging the outcome values for the points in a small local neighborhood, a local model is used. This technique is called LOES, which stands for Locally Estimated Scatterplot Smoothing. There are a number of choices that arise in local regression to tailor the smooth function that is estimated. The first choice is the type of model to use for the local trends. Using ordinary linear regression, a degree 1 polynomial is quite common. Degree 2 and 3 polynomials are also considered, which correspond to local quadratic and local cubic regression. Another choice is the weighting scheme to use. The one pictured here is a normal distribution, which is the most common, but there are many other weighting schemes possible that give high weight to nearby and low weight to faraway points. These weighting schemes are also called kernels. The third choice, and by far the most important choice, is the size of the span that determines what points are nearby to the target point. With a large span, the estimate of the function at each point is determined by a large portion of the data, so the estimated function is smooth. This is illustrated in the figure in the bottom right, with a smooth blue line. The span of 0.7 means that 70% of the data are used for each local fit. In contrast, with a small span, only very close data points determine the estimate, so the estimated function is a bit noisier. This is illustrated with the orange line, where the span of 0.2 means that 20% of the data are used for each local fit. As you can imagine, there's a bias variance trade-off with the span size. A large span results in an estimate that has more bias but less variance because the estimate is smoother. A small span results in an estimate that has less bias because it's more complex, but this results in much higher variance because the estimate jumps around much more. So far, we've mostly focused on using nonlinear techniques for modeling nonlinearity in one predictor at a time. Oftentimes, you want to be able to model nonlinearity in potentially several predictors. Generalized additive models allow us to do just that. The framework for how a generalized additive model, a GAM, is expressed follows directly from how a multiple linear regression model is expressed. A multiple linear regression model is expressed as a sum of linear terms for each predictor. A GAM is expressed as a sum of arbitrary functions of each predictor. An analyst's desire to model the data with a GAM, rather than with a linear regression model, is the desire to account for possible nonlinear relationships between each predictor and the outcome, rather than assuming linear relationships across the board. Note that a linear regression model is just a special case of a GAM. The arbitrary functions of each predictor are just lines. For example, for a 3-predictor model, f1 could be beta 1 times log of x1, f2 could be beta 2 times square root of x2, and f3 could be beta 3 times log of x3. The relationship between each predictor and the response is no longer linear because the logarithm and square root functions are nonlinear. Note that this model could still be fit like an ordinary linear regression model by just using log transformed versions of x1 and x3 and a square root transformed version of x2. Still, this GAM formulation enriches or extends the ordinary linear regression framework. This example brings up a practical question. When we want to model with GAMs, are we supposed to guess or specify the nonlinear form for each predictor? For example, here, how did we guess log and square root as being the appropriate nonlinear functions? Are those even the best guesses? A useful feature of the GAM framework is that we actually don't need to pre-specify the exact nonlinear forms. In other words, have clear mathematical expressions for F1 through FP. One example of a less rigid specification for the functions is a desire for the functions to just be smoothly connected piecewise cubic polynomials. This is a bit more flexible than saying that a variable has to have a global logarithmic or square root relationship with the outcome. And if this is our desire, we know that we can specify F1 to Fp as natural cubic spline relationships if all the x's are quantitative. In this case, we can still use the least squares framework to estimate the coefficients of the model because we're just replacing the quantitative predictors with a set of transformed versions of those predictors. Another way to less rigidly specify the functions in a GAM is to indicate the process used to construct them. For example, we could say that we want these smooth functions to be constructed via a local regression estimation process. As we saw earlier, local regression iteratively steps across the span of the data to construct a smooth estimate of an underlying trend. So unlike the GAM specifications that we just looked at, specific global variable transformations and splines, a GAM specified as coming from local regression can't be fit with standard least squares. Instead, an iterative procedure called backfitting is used to estimate F1 through Fp. The idea behind backfitting is that we make initial guesses for each of the functions and use these guesses to update the estimate for each function iteratively using the desired fitting process, which is local regression here. For example, to estimate the form for F1, we account for the guesses of F2 through Fp by forming what is called a partial residual. We subtract part of the predicted value for each case, just the F2 through Fp part, from the observed outcome. Then we use a local regression of these partial residuals versus x1 as the estimate for F1. This process is repeated to estimate the other functions and repeated for several rounds until the function estimates effectively no longer change, until the fitting algorithm converges. In summary, the GAM formulation as the sum of arbitrary functions of the predictors allows the modeler a great deal of flexibility in modeling nonlinearity. The functions f1 to fp can be pre-specified nonlinear transformations, natural cubic spline representations, or even local regression representations. With pre-specified nonlinear transformations like log or square root, and with natural cubic splines, least squares estimation can be used. With a local regression representation, the backfitting algorithm is used. In the end, the output from a GAM fitting procedure are a set of estimates for the intercept and for each of the functions f1 through fp. Let's look at a graphical example of how the output of a GAM is depicted. Say that we want to model hourly wages as a function of the year, an individual's age, and education level. A general GAM formulation is shown here. We say that wage is a function of an intercept term to set the baseline wage, as well as arbitrary functions of year, age, and education level. In particular, let's specify that these functions should take the form of estimates from local regression. After fitting the model, we obtain a numerical estimate for beta 0, which isn't shown here, and we get estimates of f1, f2, and f3, which can be depicted graphically, as shown here. Graphical representations are useful because, unlike in linear regression, there isn't a single number that can completely capture the form of the function. In linear regression, a single number, the slope estimate, completely captures what the function looks like. Here, because we used local regression representations, there isn't a closed form expression for the functions, say like log or square root. These functions are represented behind the scenes as a series of input-output pairs and shown graphically here. The red curves show the estimated functions for f1 and f2, relating calendar year to wage and age to wage. The dotted black lines on these two panels reflect the uncertainty in the estimate. For all three plots, the black ticks at the bottom indicate the raw data values for the predictor variables. The third panel for the education variable shows box plots because education level is categorical, with levels as indicated at the top of the panel, from less than high school to greater than college. The median lines of the box plots represent the estimated function. So the value of F3 is about negative 27 for less than high school, negative 15 for high school, negative 3 for less than college, 12 for college level, and 36 for greater than college level education. To use the estimated model to make a wage prediction for an individual, we would evaluate F1, F2, and F3 at the calendar year of interest, the person's age, and their education level. We'd add together these function values and the intercept estimate to get a wage prediction. Let's go over how we can interpret the estimated functions individually. Recall that in multiple linear regression, coefficients for individual predictors are interpreted while holding constant the other variables. The same idea is true for GAMs. The left plot shows the relationship between wages and year, holding constant an individual's age and education level. So we see that on average, for individuals with a fixed age and education level, wages increase over the years. The middle plot shows the relationship between wages and age, holding constant calendar year, and an individual's education level. We see that on average, individuals in a fixed year and with a fixed education level see an increase in wages with age, followed by a decrease. The last plot shows the relationship between wages and education level, holding constant calendar year and an individual's age. We see that on average, individuals in a fixed year and with a fixed age see an increase in wages with increasing education. So, in summary, local regression is another tool for modeling nonlinear trends and has conceptual similarities to KNN regression. Local regression is often used in the fitting of generalized additive models, a technique for estimating nonlinear relationships between a response and multiple predictors. Because the functions estimated with GAMs are interpreted as holding constant the other predictors, GAMs have the nice feature of being fairly interpretable, while powerfully being able to handle nonlinearity in predictor outcome relationships.